Welcome to the deep dive. We're taking the sources you shared and pulling out the insights, the surprising facts, and the essential knowledge you need to be well-informed and fast.
Today, we're digging into one of the most fundamental beliefs we have about training large language models.
Which is this assumption that to get great reasoning, you just need vast resources.
Exactly. For years, the consensus has been that if you want an LLM to perform these really complex, sophisticated tasks, you need massive amounts of high-quality data. We're talking thousands of tailored samples just to reach that next level.
And it kind of makes sense, right? I mean, historically, that's exactly how we unlock some of the most important capabilities.
Precisely. You look at reinforcement learning, for example, it's been absolutely vital. It's what allows LLMs to learn things like self-verification, internal reflection, planning,
All the good stuff.
all the good stuff. We saw it with foundational models like O1, DeepSeek R1, and Kimi 1.5. But again, all of those successes were built on huge, expertly curated data sets. The whole point was to just saturate the model with knowledge.
But the sources we're looking at today introduce a completely disruptive framework. It's called polymath learning.
And the challenge it poses is direct and, frankly, audacious.
It really is. It asks, can you achieve deep multidisciplinary impact using only one valid training sample? Not 1,000, not 100, just one.
It sounds totally counterintuitive, but they were hunting for extreme data efficiency. I think the paper calls it zero-shot generalization through one-shot reinforcement learning.
Okay, let's unpack this for you. Our mission here is to really understand how this single sample strategy works. We're going to break down 3 key findings.
First, the shocking extent of cross-domain knowledge transfer.
Second, what exactly makes that one optimal sample so effective?
And third, this revolutionary idea of sample engineering, where you literally synthesize the perfect training sample from scratch.
Right, and if we look at the context, this isn't coming entirely out of nowhere.
No, not entirely. Prior research had already hinted at this power of efficiency. For instance, the Laroe approach, less more for RL scaling, had already shown that you don't actually need all the data.
Right, they showed that a strategically selected subset, I think it was just 1,389 samples.
Yeah, that small subset could actually outperform training on the full 8,000 sample math dataset.
That's already a massive cut in data. And even more critically, previous studies had already seen that even one single sample could produce, well, small but meaningful improvements.
But those improvements were always strictly limited to the domain of mathematics.
And that observation, that small contained effect, that became the core hypothesis here.
Exactly. The researchers basically asked, what if that small boost wasn't about teaching the model a specific math fact, but about enhancing the fundamental reasoning architecture itself?
Because if it's about general reasoning, then a single sample should generalize way beyond its original context.
It should go far beyond just math.
So how is this polymath learning actually implemented? What's the setup?
It's a very clean setup, actually. The entire training is done using a specific reinforcement learning technique called GRPO, Generalized Policy Optimization.
Okay.
You can think of GRPO as a specialized variant that's known for its stability and efficiency. But crucially, the dataset, which they call polymath, is defined as just one input prompt and its corresponding perfect golden answer. That's it.
One prompt, one perfect answer. It's so simple. Before we get into the crazy engineered samples, let's talk about the natural ones they tested. Give us a taste of what kind of math problem they thought was dense enough to be a polymath candidate.
So they started with these challenging multi-step math problems. A great example is one of the algebra problems they used about polygons. It describes a 100-sided polygon, they call it PM1, on a Cartesian plane.
Okay.
And the key starting condition is this. The sum of the x-coordinates of all 100 vertices is 2009.
2009, a nice specific number.
Then the recursion kicks in. They form a second 100-gon, p-2, by taking the midpoints of all the sides of p-dollars. Then they make pt3 from the midpoints of p-2.
And the question is about the sum of the x-coordinates for T383.
Exactly. And the answer, because of how midpoints work,
It's 2009 again.
is 2009 again. It's an elegant problem. It requires understanding recursive relationships, coordinates, a very specific kind of algebraic thinking.
But the really fascinating part, which I think leads us right into the next finding, is that training on this one problem didn't just make the model better at algebra.
That's right. Once they saw a single sample could move the needle, the next logical question was, well, how far does that affect travel? And this is where we get to the core discovery. The power of cross-domain generalization.
And this is really the breakthrough.
It truly is. That single, carefully selected math problem produced significant performance gains not just in mathematics, but across totally diverse knowledge domains. They saw meaningful improvement in physics, chemistry, and biology benchmarks.
Which is just, it's wild. This completely shifts the perspective. If you only give the model one sophisticated math problem, why is it suddenly better at calculating photon energy or understanding protein structures?
So what was the secret sauce?
Yeah, what was the essential characteristic of the samples that generated this power?
They tied the sample's effectiveness directly to the presence of what they called salient math skills, skills they felt were critical to general quantitative reasoning.
Okay.
And when they analyzed the successful samples, two skill areas consistently dominated: algebra and precalculus. This strongly suggests they aren't just narrow math tools, but foundational building blocks for problem solving across any quantitative field.
So if algebra and precalculus were the key ingredients, how did they choose the best single natural sample? I'm guessing they didn't just pick the hardest one they could find.
No, actually, their selection strategy was highly counterintuitive. It goes back to that limit score we mentioned earlier.
Right, the less is more score.
Remember, the limit score measures how typical a sample is, how much its reward trajectory aligns with the average for the whole data set. A high score means the sample is a perfect, representative, normal math problem.
It's exactly what the model expects to see during typical math training.
Correct. But they were explicitly trying to avoid that narrow math specialization. So they did the opposite. They deliberately selected samples that had the lowest Lamar scores, specifically samples scoring around zero 0.6.
So instead of choosing the most representative piece of data, they chose the outlier.
The outlier. The piece of data that was just a bit abnormal, that forced the model to generalize a deeper structural principle, rather than just overfitting to standard math patterns.
That's a fantastic way to put it. They were actively seeking data that was weird enough to promote abstract generalization. And that selection strategy, it perfectly sets us up for the next logical step.
It really does.
If you can get this far by selecting a weird natural sample, why not just build the perfect weird sample yourself?
And that leads directly into this new era of sample engineering. The research argues that the future of LLM refinement isn't about increasing data volume, which they note can actually degrade generalization, but about precision design and synthesis.
Okay, this is where it gets really interesting. They decided to build a hybrid metasample from scratch, one that integrated multiple reasoning skills. How did they do that? I mean, how did they ensure quality? They had to use existing models to help construct it, right?
That's the key methodological point. You have to avoid a garbage in, garbage out situation. The construction was a two-stage process. First was candidate generation. They used the current state-of-the-art models. They cite OpenAI o3, Gemini 2.5 Pro, and DeepSeek R1 to generate and solve complex multidisciplinary problems.
So they're essentially using the world's most advanced LLMs as a sort of quality control board.
Exactly. They only collected the golden answers from problems that these strong models jointly succeeded in solving. This ensured the input problem itself was high quality, solvable, and required true multidisciplinary thinking across physics, chemistry, and biology.
Okay, so that's stage one. What was the second stage? Specialized selection. Once they had this pool of high-quality candidates, they needed to find the most polymathic one. They used another powerful model, Quen 2.572b Instruct, to analyze each problem and identify the abundance of those salient math skills, algebra, precalculus, and so on.
And they just picked the one with the most comprehensive skill spectrum.
The densest one. And that became the synthetic prime.
And now for the punchline. What exactly was this ultimate engineered problem?
The synthetic prime is it's a masterpiece of integrated knowledge. The prompt starts by describing a double-stranded DNA fragment. It's 11 base pairs long, has a specific sequence, that's the biology component.
Okay.
Then it details the bond energies. AT bases form 2 hydrogen bonds, GC bases form 3, that's the chemistry component.
So far, so complex.
Then comes the physics. It says the molecule is irradiated with monochromatic light at a wavelength of 400 nanometers. So to solve it, you need Planck's constant, the speed of light, Avogadro's constant.
3 sciences in one colon. And the final task is to calculate the minimum number of 400 nanometer photons needed to supply just enough energy to break all the hydrogen bonds in that single molecule.
And the answer?
The answer, after all that, is a simple integer.
2. Just 2 photons. It's incredible. Fusing those domains into one problem forces the model to connect physics, chemistry, and biology through a mathematical lens all at once. So how did this one-shot polymath learning using the synthetic prime actually stack up against the big data-intensive methods?
Well, the performance comparison is really telling. Comprehensive learning, the 8,000 sample set, or the 1,389 LeMR subset, it still held the top spot on pure math benchmarks like Math 500. Which makes sense, right? They're math specialists.
But the synthetic prime model was the generalist.
Generalists, exactly. The one-shot polymath learning consistently outperformed comprehensive learning on most non-math benchmarks. It was particularly strong in physics and chemistry.
So the data-intensive approach makes you a master of one domain, but the precision approach makes you a polymath.
That's a great way to put it.
What's fascinating here is the generalization depth. Did this single synthetic sample only help in subjects close to math, like engineering or statistics? Or did it boost abstract reasoning in totally different fields?
And this is where it gets really interesting. It strongly supports the idea that they were enhancing fundamental abstract reasoning. The synthetic prime's advantage was most pronounced on subjects that were semantically distant from mathematics.
Distant. Give us the numbers on that. What kind of subjects are we talking about?
We're talking about fields like agronomy, literature, sociology, non-quantitative, text-heavy domains. On the 50% farthest subjects, polymath learning yielded an average improvement of a massive 14.5 points.
Wow. And compared to the closer subject?
On the 50% of subjects closest to math, the gain was only 7.7 points.
That is just stunning evidence. It shows that focusing on the quality and density of a single sample promotes broad, abstract generalization, even in fields that aren't math-heavy. It's not just optimizing arithmetic. It's building a better internal framework for problem-solving, period.
And this wasn't just for small models. The benefits extended to larger platforms, too. When they tested it on models like Qwen 2.5 14b base, and even on highly tuned models like OctoThinker, the single synthetic prime still outperformed comprehensive learning on really demanding multidiscipline benchmarks.
Okay, let's shift focus to how the model was solving problems after this one-shot training. What did they observe about the reasoning mechanisms themselves? I mean, did it think differently?
It did. The RL training clearly induced these sophisticated self-verification patterns in the responses. When they analyzed the reasoning chains, specific checking terms started popping up.
Like what?
You'd see, wait, verify, yet reevaluate and recheck. It was as if the model was pausing itself mid-thought to double-check its work.
And did those checking mechanisms vary by subject? Did it prefer verify for one thing and reevaluate for another?
They absolutely showed domain preference. The term verify was heavily preferred when the model was dealing with pure math problems. That appeared significantly more often when the model was tackling science and engineering problems. It suggests maybe a need to reassess physical parameters or chemical properties.
What about using code blocks? We know LLMs use internal code execution for tough problems.
That usage varied, too, and held a key nuance. Interestingly, the initial natural sample, the one based on intermediate algebra, actually prompted the most code blocks overall. But how the code was used was different.
In what way?
In physics and chemistry, the code was used mostly for result validation. The model would do the step-by-step reasoning, then use a Python script to check the final number.
A safety net.
A safety net. But in pure math problems, the code was often used for final answer generation itself, which sometimes led to execution failures like timed out. The model was relying on the code to get the answer, not just to check its own thinking.
That's a huge distinction. Can you give us an example of the model using that self-verification as a safety net in a complex scientific context?
Of course. They show it with a tricky chemistry problem about the Joule-Thomson coefficient, often shown as the Greek letter mu.
A highly non-trivial calculation.
Oh, yeah. It measures how the temperature of a gas changes with pressure. The model tackled this by first using the thermodynamic formula, the one with enthalpy and partial derivatives.
Right.
After completing that initial complex calculation, the model explicitly called for and used a Python script to verify the algebraic steps and the final numerical result.
Yeah.
That's the hallmark of the self-correction mechanism in action. Theory first, programmatic check second.
This deep dive it's fundamentally challenged the idea that quantity is king in AI training. The ultimate summary here seems to be that data quantity is no longer the sole dictator of an LLM's reasoning quality.
That's the major takeaway for you, the learner. Precision, embodied by polymath learning and the art of sample engineering, can achieve superior, broad, cross-domain knowledge transfer. By focusing on designing a single, dense, multidisciplinary sample like the synthetic prime, you can efficiently unlock generalized reasoning, completely bypassing the need for thousands of examples.
It's a huge step toward training smarter models faster and with far less data cost. But here's the interesting disconnect and our final thought for you to explore.
Go on.
While the study clearly showed that different polymath samples triggered these distinct self-verification patterns, like preferring reevaluate in science versus verify in math, the researchers explicitly stated that they did not observe a direct connection between those checking styles and the actual improvements in reasoning.
Precisely. They're seeing the behavior, but they don't yet understand its direct impact.
So the question remains for you. Are these sophisticated checking mechanisms just a fascinating side effect of better training, a symptom of heightened intelligence? Or is there a specific optimal internal verification style, a hidden syntax of self-correction that, once we discover and target it, could yield even greater and more reliable reasoning gains? Something to think about as these models get smarter with fewer and fewer inputs